Hello all and welcome to this final video presentation for the Eye in the Sky project. If you happen to be watching this in class on Tuesday right now, my apologies in advance for not being there. I am actually most likely on a flight at the moment if all has gone well, but we'll call it Project Field Research and I hope that this will be enjoyable nonetheless. So before I get into the interesting things, I'll just do a brief introduction. I'm Jonathan Klingspun, a first-year CS PhD student, and you can kind of say the sole proprietor of this project. I have some background in embedded vision from working at a startup founded by several CS PhD alumni, and so I thought it'd be fun to kind of try the whole process for myself for once, and so... Flying is rather difficult, requiring many hours of very expensive training in order to get a license, and just one of the many challenges in aviation is visibility and situational awareness. Of course, when there are other aircraft nearby, either on the air or on the ground, a slight lapse in this awareness can have some rather dangerous consequences. Systems have of course been designed to mitigate these dangers, such as the Traffic Collision Avoidance System, known as TCAS, which provides a minimalistic radar-style view of the nearby airspace. However, in small-scale aviation, such as single-engine aircraft or even UAVs, these systems can be prohibitively expensive and are not mandated all the time for installation. But perhaps it's possible to create a cheaper, more intuitive option for this market. Real-time flight telemetry is free and readily available at a pretty high sample rate, as you may have seen before on websites such as FlightRadar24. This data is provided directly via radio signals from aircraft transponders in an unencrypted digital format known as ADS-B, so other planes or ground facilities such as air traffic control can track the surrounding airspaces, so making use of this provides a natural first step in implementing any kind of plane tracking system. Everyone is of course also by this point familiar with GPS, or more broadly GNSS, which provides the accurate location of a receiver using satellite constellations. So now you know your own location, the location of a plane, and you could do some simple math to find the relative distances. Congratulations on completing half the project. For visualization we had a machine vision camera, and then a compute board to do some slightly less simple math. With some notion of camera geometry and the relative positions of the aircraft to the viewer, we can back project these 3D positions onto the 2D image plane. I highly recommend Professor Ochoa's CSE 252A if you're into that sort of thing. So now we could get to actually implementing.
You'll work off that cake in the acid mine!
First I'll go over the hardware used and all the terrible choices that were made. This whole project is mostly made of parts I had lying around. So I'll start with the radio parts. I used an RTL SDR, which is a standard and inexpensive software-defined radio receiver, which can be tuned to 1090 MHz to receive ADS-B directly. These are very well supported and have plenty of libraries to interface with them and receive and decode ADS-B. After that is the Septentrio Mosaic X5 GNSS receiver, which provides unnecessarily overkill precision in this case, which is attached to a Talisman helical antenna. For compute there's a Raspberry Pi 4B, which you all know very well. And finally a Vision Components IMX565 MIPI camera, which provide me with only pain and suffering. More on that later. One thing I'll kind of touch on briefly is my custom Linux distribution Skynix, which I created using Buildroot, which is a tool that allows you to generate an entire Linux distribution from specifically defined configuration files. This integrates well with CI/CD pipelines, allowing me to rebuild a new image every time changes are made. So now back to the flashy things, here's the mechanical design of the system. This is the part where I learned that a single time using SolidWorks about 5 years ago is less than sufficient for completing a full system design in a timely manner, and this ended up being by far the most time-consuming part of the project. This enclosure has the fun feature of a two-part design of an upper housing for all the RF-sensitive components, which can be shielded from the lower housing, which contains the compute board, camera, and some very noisy connectors. To manufacture, I did some 3D printing at the lab, which went a little bit poorly the first time, but fortunately I was able to beg a friend to borrow his Bamboo X1 Carbon, which printed it successfully, and eventually I had the complete unit, after some drill pressing. So finally, it's time for... Final integration involved getting everything working while it was put together. GPS just kinda worked, so not much to do there, thank you Septentrio. While trying to test some artificial ADS-B data by direct connection to the receiver, to not anger the FAA and FCC, I managed to toast my RTL SDR on the device, and had to overnight a new one. Lessons in desktop RF attenuation are often learned the hard way. After that I discovered the Vision Components driver for their cameras on the Pi does not at all integrate with the hardware-based image signal processing, meaning had giant Bayer images no way to debayer quickly. I solved this by pyramidizing the image down, which is computationally efficient, getting grayscale images, and questioning my life decisions. All I had to do at this point was calibrate the camera, convert the GPS coordinates to UTM, or convert Latin long to distances in meters, do some of the aforementioned less simple math, and it actually kinda worked. This pointed towards Palomar Airport directly north of me, and I'm getting plane data projected onto the screen. For a little bit anyway. Turns out I'd vastly overestimated both the Pi's power delivery ability and compute speed, and it was not happy with me. But such is life in embedded systems. Thank you all for watching, I hope you learned something or at least found some entertainment in my chaos. I know I certainly did both. Thanks again.